In the last video, we learned all about streams and how they're implemented. We also saw an application for lists and streams that involves finding the second prime number between 10,000 and a million. So in this video, we're going to learn about using streams, and we're trying to work our way back to solving that primes problem using streams. Now, in order to do so, though, we'll first have to implement all of the relevant helper functions. So let's start by implementing the stream range function. So define stream range, and that's taking in two values, call them a and b, or start and end, whatever you like. So a is a low value, b is the high value, and we want to create a stream of all of the integers between a and b inclusive. Now, the thing about streams, though, is that they're implemented as a delayed pair. We don't want to compute all of the values between a and b. We just want to create a pair between the first value and a promise to compute all of the other values. Now, it just so happens we have a function that can do that delaying promise part. We just need to know what to put into that promise. So, stream range here has a start and an end value, so we're going to have a condition. If we reach that end value at some point, because remember, somebody's going to be using this range eventually, then we'll stop. So if start is ever greater than end, then we'll return the empty list. So an empty stream is just an empty list. The last value in a stream is the same as the last value in a list. And the rest of this code is going to be structured just like normal recursion. We're going to have a base case and a recursive case. So here's our base case. And in our recursive case, we want to construct a stream with a promise that can recurse to create these other values. Okay, so we'll have a stream cons that starts with our first value. So a, sorry, I'll call these a and b, not start and end. So we have stream cons that starts with our first value, and then the promise here needs to be a promise to compute all of the other values. Now, it just so happens we have a function that will compute all of those other values called stream range from a plus 1 to b. Okay, so this stream con says compute this first value a. Let's say a and b are 1 to a million. A will be 1, and then what it will return is 1 dot and then a promise to compute all of these other things. Remember, stream cons says cons a to delay b, right? That's all up here. Cons a to delay b. So this would be the second argument into our stream cons. So stream cons a, where a is 1, to a promise to call stream range on the remaining values from 2 to a million. Okay, so let's test this out, see what happens here. So if we run our code, we can say stream range 1 to a million. And there we go. 1 dot promise, and it happens very quickly because it's actually just saying 1 dot and then a promise to figure out what the rest of that means later on. So it's just creating a pair, and that's all it has to do. It doesn't have to go through all million values and construct a list of a million elements. It just says create a promise, don't look at the rest, we're done. Okay. So there is 0 recursions occurring in this first implementation, right? When we call stream range, this stream cons is just going to return a pair right away. The recursion, this stream range part, doesn't actually happen because it's being passed into a delay. Now later on, when we force this stream, we're going to find the CDR of the stream points at a promise to do all of these. So when we force it, we'll actually execute that promise, which calls stream range on 2 to a million. So if a is 2 and b is a million, that's still false, and we'll come down here and say stream cons 2, and then a promise to compute from 3 to a million. Okay, so let's actually see a quick substitution model here. Will help illuminate this and other functions. So if I said stream range 1 to 100, a little bit less typing, this becomes stream cons 1 to stream range plus 1, 1, and 100. Okay, and because stream cons returns a pair, we'll get 1 dot promise. That is the entire execution. So if you want, we can put this extra step in here, what happens inside stream cons. This gets translated by special form to essentially cons 1 to delay all of this, delay and cons, which then becomes 1 dot promise, makes it a bit clearer perhaps. Okay, so what I'm going to do is, instead of putting this in as a promise, in these substitution models, I'm going to use a slightly different structure here. I'm going to take the stuff that was delayed and sort of make it visible here. So I'm going to use square brackets to to indicate delayed code. So one.promise, this isn't actually going to run, this is just what's in the promise so we can see it a bit clearer. That'll help when we're working with these streams if we want later on. Okay, so if that's all that happens when we call stream range, what happens if we call something like stream CDR on the stream range from 1 to 100? Okay, so the first step we've already seen. So this becomes stream CDR on stream range, stream CDR on 1 dot, and then the promise to compute stream range from 2 to 100. Notice it doesn't even compute the +1, 1, so it's going to get a bit messy. I might simplify that later. But for now, let's just keep it as explicit as possible. So stream CDR of 1 dot all of that. Now stream CDR says two things, right? This is a function that says taken the CDR of the stream, so that's this part here, and then force it, which means essentially turn these square brackets back into round ones and evaluate. So the stream CDR becomes, I'll type it all in detail for this first time through, force the CDR of 1 dot, and then all of this. Copy 1 CDR and force, okay. So then evaluating this in the same normal way, we have a pair here, and we want the CDR of that pair, so that's going to be this block here. So we have force this pair, and then when we go to force that pair, what happens is we essentially just turn that expression into a round bracket expression. So we get stream range +1, 1 to 100. Okay. And now the next step from that is, as we normally call a function, stream range, you need to evaluate the sub-expressions first, and then we can apply, and that becomes, goes up to here, and we get the body of stream range, which again calls back to stream cons. So we get stream cons 2 to stream range +2, 1, 100. Close. Okay. Right, and then this sort of, we can walk through all that if you will, but I feel like we understand the rest of this now. So this is essentially where we were here. That creates a pair to a promise to compute the rest of that. Okay, so ... I'll leave you to fill that in, if you will, later on. So that's the idea behind stream range and working with streams in general. So, stream range and working with streams in general. So each time we're creating a stream, we're actually just doing a single step. We're creating that pair and then delaying what comes next. So stream cons here, be very cognizant of the fact that stream cons is where the delay occurs. So stream cons 2 to all of this, or stream cons 1 to all of that, creates a pair, 1 dot, and then a promise to compute whatever comes next. All right. Also worth pointing out here, so this is the code for stream range. Let's see if we can't also take the code for range. It's a different version. Let's implement real quickly just list range here. So define, I was going to call it range again, AB. For list, if we were just using the recursive version, not the iterative version, it would look something like this. If A is greater than B, return the empty list. Otherwise, cons A onto the range plus A1B. Right? So with the recursive list structure, without using stream cons, what we have is a cons, which becomes a delayed operation, because before we can execute that, we have to, it becomes a deferred operation. I should be very careful with that word. Because the range function needs to be evaluated first, because we have applicative order, because cons is not a special form, we first evaluate this function here, this call to range with 2 and 100. And that calls 3 and 100 and 4 and 100. We end up with these sequence of delayed conses where we have cons 1, cons 2, cons 3, cons 4, all the way down to eventually we get this empty list, and then all those conses collapse and we get a big list structure. But notice the difference between these two functions is really just stream hyphen. Okay, so in terms of the actual code that we typed, because we're using stream cons, we get very different behavior, but the rest of the code is just stream and then cons, right? Where we have range, we have range. Where we have a call to range, we have a call to range. Where we have cons, we have the regular cons. The same will be true of car and CDR. When we're implementing functions that work on streams, they end up working the exact same as they would on lists. The behavior is very different, obviously, because we have that delayed evaluation, but the text of the code actually ends up being analogous. It's handy to remember if you're trying to implement some stream function. You can work the list function out first if it's easier in your mind to not deal with all these delays, and then just translate that into the delayed form for streams. All right, so let's do another practice. This one isn't actually going to help us get to our primes problem, but it'll help us understand the filter function when we get to it. So let's do a simple function, StreamRef. So StreamRef is a function that returns the nth element in a stream, similar to how it works for lists. So recall, if we're working with regular lists, if we want the nth element in a list, we just CDR down n times, and then we can return the car of the list. So if we want the 0th element, we CDR 0 times, we return the car. That gives us the first element in the list. If we want element 1, we CDR 1 time, then return the car, and we get the second item from our list. Okay, so it works the exact same for streams. So let's implement that here, and then we can walk through the substitution model, try and get the knowledge or the understanding behind it as well. So StreamRef of some stream, and we want some integer n, so like this. So we want the nth integer out of this stream. A few different conditions here. So either we have an empty stream, in which case the item wasn't there. So if EQ the stream empty list, or if you want, you can say if null stream, then in that case, well, the item's not there, so we'll just return false. Okay, so if somebody asks for the 10th item out of an empty list, well, I can't do that for you, I'm sorry. Okay, so that's one base case, it's the failure base case. The next will be the success base case, and that's once we've CDR'd down this list/stream enough times, we've gotten to the item we're looking for, so we can just return that. And that will be marked by this integer n. So if they want the 4th item, we're going to be CDRing down 4 times, but we'll also subtract 1 from this value 4 times. So by the time we get to the item we want, n will equal 0. So if equals n 0, then we can return the first item. So the stream car of stream, which again is just the car of the stream. Okay. And then our recursive case. So else. Now, again, if we're dealing with the lists, it's pretty straightforward. We just want to CDR down until we get to the right spot. When we're dealing with streams, we're not doing any delays here because we're not constructing anything. We're consuming a stream rather than producing one. So this actually works very similar to the implementation for lists as well. We're going to say StreamRef on one smaller value, so minus n1, and on the one smaller item in our list, so stream CDR of some stream. Okay. So the real trick here is figuring out what does stream CDR do that's different than lists CDR. Okay, so with stream car, that's just essentially the same thing as car, but with stream CDR, it has that force in there. So let's walk through a substitution model here. So if we have something like StreamRef 3 for a simple range, like stream range 5 to 10. Okay. Now, I'm not going to go through all the stream range stuff because we've already seen how that works. So if I said something like StreamRef 3, stream range 5 to 10, we know kind of already creates a delay or a promise. And that creates essentially a pair, 5 dot, and then stream range 6 to 10. There, okay. So that creates a pair between the first item in that list and a promise to compute the remaining items in that list. Okay, so then what happens next? Well, the next thing is we pass all this information into StreamRef. StreamRef says, is this stream empty? It is very much not. It's a pair that has a value. Is n equal to 0? It is not, so we're into the recursive case here. And that says call StreamRef with n minus 1, so minus 3, 1. And with the stream CDR of the stream 5 dot stream range 6 to 10. Technically it's 5 plus 1 to 10, but for simplicity in typing, I'm calling it 6 to 10. Close and close. Okay. So let's clean up this line a little bit. So the stream ref of 3 minus 1 is 2, and the stream CDR, this, remember, gets translated. Scroll up here to the stream CDR. Gets translated into this, essentially by substitution, just using regular applicative order. So that becomes force the CDR of 5 dot stream range 6 to 10. close the stream, close CDR, close force, and close the ref. Okay, so we can simplify this line a bit more. So StreamRef 2, the CDR of this pair is just this block here. So we're going to say force, and then take this block, and that's what we're forcing, the CDR of our pair. And if we were to force that, we'd get StreamRef 2, stream range 6 to 10. Okay. Now notice this is the exact same as our first step here, right? So we're going to go a little bit quicker from now on because these intermediate steps are going to be the same for every other stage here. So we're back up at the top essentially with smaller values. N is now 2, and our range is now 1 item smaller. So the next time through will be StreamRef at n minus 1, which would be 1, and the stream will be 1 item smaller, so stream range 7 to 10. And then again, StreamRef 0, stream range 8 to 10. And then finally it can return the car of that, so we can say 8 in that case. All right. So hopefully that makes some sense. Actually, let's show that last step just for the notes here. So that becomes stream car from this thing that comes out of stream range, which was 8 dot the promise to do stream range 9 to 10, something like that. And then we can return 8 because that's just a pair, so we return the car of that pair. Okay, so that is the StreamRef function, and it's not too different from the list function. Again, take a look at how we implemented the list version of this, and it'll be pretty much the same, except we'll have car, list_ref, and CDR. Instead of having stream hyphen, we'll just have the list and analogs of those same functions. The only real difference is in the actual execution of that. We have this stream range that doesn't actually return all the values, so stream CDR has to consistently say, take the thing that came out of stream range, so this, where is it here? This pair, 5, 6 to 10. Take the CDR off of that, and then force that CDR so that we get the next step in our range. So rather than just simply pulling the next element from our list, we have to actually compute the next element of our list. But we're only doing one at a time, so it's ultimately saving us some time if we don't need all of the values. Okay. So with that in mind, we're ready to learn the stream filter function, which again works very similar to the list filter function. So define stream filter, very similar to the recursive list filter function, I should say. So stream filter takes in some predicate and some stream and returns a stream that has just those values. But now when returning a stream that has just those values that pass the test, in this case means returning a stream that has the first value that passes the test and will compute all of the remaining values when required. So let's type this out and then we'll walk through it. So the first case is our base case. So either the list is null, or stream is null, sorry. If our stream is null, then we filtered all the values out, problem solved. We have one case for if the car of our stream passes the test, so we'll apply pred to the stream car of our stream. And if that's true, then we will, oh, it's not going to tab for me. Okay. If that's true, then we will stream cons two things. First off, the value that we just pulled off, so the value that we want to keep, stream car of the stream again. And the other value is the recursive call to checking all of the other values. So in this case, stream filter, the predicate, and the CDR of our stream. So stream CDR strm. Okay, so a bit big. Close that line. Let me just format this so I can get it all in one line with this font size. Nope, it didn't work. Come back to me. Oh, it got deleted. Here, let's do this. Okay, so in the case that the stream car passes our predicate, so it's a value that we want to keep, so it is a prime number, for example, then we'll stream cons that value with a promise to compute the rest of these things. So remember, stream cons is what causes that delay. So out of this won't be a recursion. They won't have a deferred cons operation building up on the stack. Instead, what we'll get back is a pair between this value and a promise to do this. Notice this promise has two things in it. It has a promise to compute the stream filter, but it also has a promise to compute the rest of the stream. So if the stream that was passed in was, for example, the range, we haven't generated all the values from 6 to 1,000,000 yet. We've just found out that we wanted to keep the 7 value, let's say. We still have to compute all those other values. So we still have the stream range in here of uncomputed values. And on top of that, now we're going to wrap that inside a filter that will, as we're generating those values, remove the ones that aren't good. Okay, we'll see that in the substitution model in a second. Let's get our final case here, though. So base case is the list is empty. One success case is that the item that we're looking at passes our test, in which case we're essentially done. We can just return the stream. Here's one value, and I can compute the rest later. The other recursive case is that the car of our stream doesn't pass our test. And in that case, we'll do what we did in our list. We'll just recurse without including it. So we'll say stream filter on the pred and the stream CDR. So this says call the next step of stream filter, and that happens immediately. Stream filter is not a special form. There's no delays built into it. So it immediately goes to stream filter with the CDR of our stream. So if that stream was the range from 7 to 10, we're now looking at the range from 8 to 10 as the next set of our values. Okay, so stream CDR, remember, forces the next element out of our range. All right, so let's test this out first, and then we'll walk through it. So run our code here. So let's do a stream filter. We want just the even numbers in the stream range 1 to 100. We get 2.promise. So it finds the first value and then stops. All right, anything else I need to say about this? Okay, nope, not so much. It is worth pointing out or taking a look on your own time. Take a look at the recursive version of the list filter. You'll see it is very similar to the stream version. Again, pretty much the main difference, in terms of the text typed at least, is just stream hyphen in front of cons, car, and CDR. Everything else is pretty much the same as it was. But that stream hyphen is very important because we go from having cons as a function to having cons as a special form with a delay. So instead of having this recursive operation happening first, we have a delay happening that pauses this recursive operation until the user requests the CDR in a future operation, or in a future expression. Okay, so we've tested this out. Let's see the substitution model. A good example for that? Sure. Basically what I just typed there. So stream filter. We're going to stream filter out all the even numbers from the stream range 1 to 10, we'll say, for shortness of typing. Okay, so stream filter is not a special form, so we have to evaluate the sub-expressions. So this becomes stream filter, and then whatever comes out of stream range 1 to 10. And again, you can walk through all the steps to see what actually comes out of that, but we've seen pretty much just this happens, right? 1 dot, and then a promise to compute everything else. So effectively, that's what goes here. We have stream filter 1 dot, and I'm going to put in square brackets to show what's in that promise. The stream range from 2 to 10. Again, it should be +1, 1, 10, but 2 to 10 is easier to read, so I'm going to use that for this mental model. Okay, so next step is we can actually apply this stream filter function onto that. So just going to the active branch of our cond, this is not the case, right? Our stream is not empty. Does the car pass our stream? We'll say 1 is not an even number, so that's false. And then it comes down to here, and then that becomes stream filter. Stream filter, filter even, so we're passing the pred through. And then the last argument becomes the stream CDR. So we have the stream CDR of 1 dot, and then stream range from 2 to 10 as it was. Okay, we can clean this up a bit. Stream filter even. Now we've seen how stream CDR works a few times, so I'm not going to do it the long way here. Again, it takes the CDR of this and forces it, so I'm just going to copy this, paste it here, and change the square brackets to round ones. And now we can see our stream filter, or our expression, has sort of come full circle, and we're now there again. So we call stream filter again on the next range, so we need that next range first, actually. Stream filter even 2.promise to compute the rest of this range 3 to 10. Okay, now we have everything as simple as it can be, so we apply. So stream filter on this list again. It's not an empty list, but the stream car, which is 2, does pass our test, which is even. So we end up getting this expression. I'm sorry, this expression. So that is stream cons, the stream car of our stream. I'm going to type it out in long form for this first step here. 2.stream range 3 to 10. Okay, this is definitely going to go off the screen. That closes the 2 and the stream car. And then, so that's the first part of our cons. And the next part of our cons is stream filter all of this. I'm actually just going to grab all of this. Oof. Okay. So stream filter, the pred here is the even predicate. Stream CDR on some stream, where again the stream is this thing here. Just make this full screen so we can see it all. Okay. So this is our expression now. It's gotten a bit big. We have stream cons to the car of this stream. So attach the car of this stream onto the result of doing all of this. Now, because it's a stream cons, though, we're not going to figure out what that result is. So instead, we're just going to delay all of that and get the car of this dot a promise to compute all of that. So remember, stream cons becomes cons. Oh, sorry. That's not a special form. Oh, it is a special form. Cons, the stream car of 2 dot stream range 3 to 10 onto all of this. Rather than typing it again, let's just copy and paste. Oh, actually, it will be faster, more accurate if I type it proper. So it's cons A onto delay of B, where B was stream filter even stream CDR 2 dot stream range 3 to 10. Okay, so close the stream, close the CDR, close the filter, close the delay, and then close the whole cons. Okay, so that gets us past the special form. Remember, the special form translates its inputs to its outputs without doing any sort of evaluation. So both A and B technically get unevaluated. Now when we do this cons is not a special form, so we walk through these evaluations. So we get cons, the stream car of all this, which I'm just going to jump to the answer, is 2. And delay of all these things. So we essentially take this block of code here, which I think I can highlight. Oh, not well, it's in comments. Okay. So we want the 2, the CDR, and the filter. So all of this, where the outside brackets become square brackets to represent that they've been delayed. So cons 2 to all of that, which ends up giving us 2 dot promise. So when we type this expression, similar to how we typed it there, it computes up until it finds a value that passes our test and returns that promise. Now, if we ask for the CDR of this promise, it has to evoke this, this delayed expression, this expression here. But evaluating that expression isn't too confusing because it's pretty much the exact same thing we just saw with all these other ones, right? Stream filter even from some part of this range is very similar to this line here, for example. So it continues on the same pattern as we've already seen. Missed a bracket. Okay, so that's the stream filter function. Again, the code for the stream filter function works a lot like the list version, just with stream hyphen in front of all of our function calls. But the behavior of it works very differently. It computes until it finds a single value that passes our test, and then the stream con says, well, we got one value, so we'll take that as our car, and then we'll make a promise to figure out what all the other stuff is. But now notice inside this promise is a nested promise, right? The promise that we see here is a promise to filter the remaining values from the range, but we haven't yet computed those values from the range yet. So we have a nested promise wrapped inside a promise to be filtered, all those values, and that gives us ultimately this stream. So we're delaying a lot of effort later on, but for now we've done very little and we've gotten the answer that we were looking for. So let's finally see how this works for our large problem. So recall when we tried solving this, this problem of finding the second prime between 10,000 and a million, we tried doing that using using lists, and it was a lot of extra work. But we can see now how streams work. We have now range and filter functions for this. So let's walk through the implementation. It's going to look exactly the same, actually, so I don't have to walk through it. We want the stream car of the stream CDR of the stream filter using prime. That part doesn't care what value it is, or what type of structure it's coming out of. using the stream filter prime over the stream range from 10,000 to 1 million. Okay, so a little bit more verbose because you keep having to type in stream hyphen instead of just car, CDR, and what have you. But let's see how quick this is. 10,009, just like that. So, as we can see, in some situations at the very least, having a delayed operation or a delayed evaluation for these very long sequences of lists saves us a lot of time if we only need the first few values. If we can maintain this abstraction that all the values are there, so long as we're only accessing the first one at a time, we can compute the new values on demand. So whenever somebody says stream CDR, well then before we give them back the answer, we'll figure out what that answer is and then give them back that answer. But we'll only ever do one step at a time, so you never have these very large delays between processing, trying to get through all the values when all we need is the first one. All right. So that's the idea behind using streams, but the real power of streams is unlocked when we consider that they can go on forever. Okay? So because of delayed evaluation, streams can be processed before they've ended, right? We can compute the first value without having to figure out what all the other values are. And then we can filter the first few values before computing out the end of our list anyways. So a stream can represent a sequence that has no end, and we can process the values of that sequence one at a time without necessarily ever needing to reach a base case. Okay. So the idea here is just like regular streams, but instead of including a base case in our construction, we just won't do that. That way, if somebody asks for the next value, there will always be another value. So let's start by creating a stream of infinite integers. Down to the bottom of all this again. So something like define ints starting from I. So it's just a function that's going to return a stream that has all of the integers starting from some input integer. Okay, so we'll have stream cons. Now the first value in this should be I, so stream cons I. And then the next value, if we're just dealing with integers, would be I plus 1. So it would be ints starting from plus I1. So this is very similar to our range function. We find our stream range. There it is. Stream cons I to the function call that will get I plus 1. The only difference here, though, is stream range has a base case. If A is greater than B, then for some reason we need to stop, because those are the only values that the user wanted. In this case, though, we don't have that. We have a starting value, no ending value. So we'll stream cons the first value to a promise to compute all of the other values, but all of those other values are just the integers starting from the next integer. And it can just keep going in that way until we run out of representational space on our computer. So we can keep going that way for a very long time in Scheme. All right, so if we run this, let's try running our code here, and we can say ints starting from I. Int starting from, and let's give it an actual value. So in this case, we get one dot promise. If we want, we can take from 2 or whatever. But the key here is that what this gives us is a stream of all those values. So we can actually say stream CDR of the int starting from 2. And that should be 3 dot promise. And if we keep doing that, stream CDR, we can keep CDRing down this list, and it's just going to keep pumping out 4 dot promise and 5 dot promise and 6 dot promise. Just keep giving us the next value. It will never reach a point where evaluating that promise results in a base case. So essentially, this stream lasts forever. Now, we'll only ever be able to work with part of the stream because we exist in a finite reality. But for most intents and purposes, we should have the ability to consider these things as infinite streams. Now, consider what would happen, though, if instead of stream cons here, we just used a regular cons. I'm actually going to give you a second to consider this, so pause the video, think through it. What would be the case here? What's the result of evaluating this function if I were to say ints starting from 1? So pause the video, think this through, and welcome back. So what would happen here? If I ran int starting from 1, this 1 goes into I, and it says cons 1 onto int starting from I plus 1. Now remember, cons is not a special form. It's just a regular function, which means it follows the eval apply, which means evaluating the sub-expressions before applying. Evaluating the sub-expressions results in a recursive call, which ultimately results in a recursive call, and again and again. A recursion with no base case gives us an infinite recursion. So in this case, if I ran this code, we should get an infinite recursion right up until Stack Overflow. There it goes. So because we have all these deferred conses, they're taking up space with each step, so eventually we run out of memory and the whole thing crashes. When we're dealing with streams, on the other hand, that's not the case. If I say stream cons I, I'm only ever dealing with a single pair, so I'm never going to fill up the call stack with a bunch of deferred conses, because as soon as I say stream cons, that returns a pair of these two things, I and a delayed variant of the recursive call. And then when we stream CDR, we take one more step and one more step and one more step. So we're never actually building up anything on the call stack, so even though stream cons and cons look and somewhat behave similarly, there's some very clear and important distinctions to be made. All right, so some stream operations also work on these infinite streams. So for example, we can filter out some values. Let's define a stream called sevens as the result of stream filtering. I'm going to create a special lambda here that finds all the values that are evenly divisible by 7. So we'll take in some value x, this will be our predicate here, if equals modulo x7. So if x mod 7 equals 0, then that's true. And that will be our predicate for determining things. And then we'll take the range of streams, or the range of integers here, from 1 to infinity. Starting from, oops, that needs a bracket. Ints starting from 1. So if we run this and ask what is the value of sevens, oops, what's the value of sevens? We get 7.promise. And if I want the CDR, sorry, the stream CDR of sevens, I get the next value. And we can keep doing that, and we'll get just values that are multiples of 7. Okay. So the stream filter function still works on that on this infinite stream. The only key difference, if we go back to our substitution model here, is instead of having a promise that's nested inside our filtering promise, we have this generating promise, if you want to call it that. The generating promise before, when using range, had an endpoint, but the generating promise here will just be int starting from 1, so it's just an infinite stream. But it's only still ever going to be a pair, so we can still filter one element at a time as needed. All right, so we're essentially wrapping these promises in a pipeline of other promises. Worth pointing out one last example here. Actually, never mind. That'll be in the practice problems at the end of this chapter. So that's it for this video, and I believe that's it for this chapter as well. A nice short chapter where we talked about streams, this lazy form of data structure, or a lazy form of sequence or list, where we only ever compute the first value and delay a promise to compute the rest of them. So that's it for this chapter. In the next video, in the next chapter, we'll learn about mutable data finally. We'll allow the operations of variables to actually consider changes of state. I'll see you in the next video.